Imagine taking a solid shape and attempting to compress every interior coordinate outward until the entire mass occupies only its own outer boundary. This compression is physically impossible within a continuous system. To force the entire interior of the disk onto the edge, you would have to tear a hole in the center of the space. Topology categorizes these qualitative rules of stretching and tearing. Algebra handles the rigid quantitative exactness of equations. The fundamental theorem of algebra provides an absolute numerical certainty. Every non-constant polynomial must have at least one complex root. It must eventually equal 0. These two fields appear to operate on different logic, yet the physical impossibility of tearing a geometric shape provides the rigorous proof for the existence of these absolute numerical roots. The connection becomes clear when we stop treating equations as a series of calculations and view them as continuous geometric mapping problems. We will use the derivation established in James Munkres's foundational text, Topology. This text provides the academic standard for the rigorous logical deduction required to link spatial behavior to algebraic outcomes. We are focusing on the transition point in the curriculum where general topology provides the tools for algebraic topology. We are connecting two specific chapters, Section 55 on retractions and Section 56 on the fundamental theorem of algebra. By following Munkres's logic, we can bypass simple analogies and rely on pure geometric intuition to bridge these two subjects. The primary tool for this proof is a specific type of mapping called a retraction. Formally, a retraction is a continuous map from a space X onto a smaller subspace, A. The mapping must leave every point already in the subspace exactly where it started. Points in the larger space flow into the subspace, but the subspace itself remains anchored. Continuity is a strict requirement. The transformation must happen without any jumps or breaks in the space. If a mapping requires a point to teleport or the space to fracture, it fails the definition of a retraction. A retraction is a test of structural integrity, proving if a space can be compressed into a smaller version of itself while remaining intact. We apply this test to a solid two-dimensional disk, d², and its one-dimensional boundary circle, S1. Our objective is to find a continuous mapping that pulls every interior point of the disk outward until the entire mass sits on the boundary ring. As the interior points are pulled toward the edge, the geometric strain increases, centering on the exact middle of the disk. To reach the boundary, the center point must tear. This rupture violates the law of continuity. Munkres formalizes this as a theorem. There is no continuous retraction of a solid disk onto its boundary circle. This geometric limit is an absolute rule we will now use to force specific algebraic outcomes. The Brouwer fixed-point theorem is a direct consequence of this geometric constraint. It states that any continuous mapping of a disk into itself must leave at least one point absolutely stationary, a fixed point. To prove this, we assume the theorem is false. In this scenario, every point moves, meaning for any point x, the mapped point f of x is never the same location. Because x and f of x are distinct, we can use them to define a unique directional vector for every coordinate in the disk. We draw a ray starting at the mapped point f of x, passing through the original point x, and hitting the boundary circle. The exact spot where the ray strikes the boundary becomes the result of our new mapping function. If no point is fixed, this construction allows us to map every single point in the interior of the disk onto the boundary circle. This would constitute a successful retraction of the disk. The exact action we proved was topologically impossible in the previous scene. Since the retraction cannot exist, the assumption that no points are fixed must be false. At least one fixed point is guaranteed. We now apply this same logic of mapping and geometric holes to complex polynomials. Proving the fundamental theorem of algebra requires showing that for any polynomial, there is an input where the output is exactly 0, the origin of the complex plane. We treat the polynomial as a mapping that transforms circles in the input plane into paths in the output plane. We assume the theorem is false, that the polynomial's output never equals 0. When we use a massive input circle, the highest power of the polynomial dominates. For a polynomial of degree n, the output path loops around the origin exactly n times. As we shrink the input circle down to a single point, The output path also shrinks until it becomes a single point. It now loops the origin 0 times. Because the polynomial is a continuous function, the path must smoothly untangle from n loops down to 0 loops as the radius decreases. A loop cannot change the number of times it wraps around a point without passing directly through that point. By assuming the polynomial never hits 0, we have blocked the path from untangling. The untangling is impossible unless the path passes through 0. Therefore, the polynomial must hit the origin. It must have a root. These two proofs rely on the same geometric mechanic. In both cases, the mapping fails because it attempts to bypass a structural hole. The disk cannot compress to its edge without a tear, and the polynomial loop cannot untangle without hitting the origin. Topology provides the structural framework that dictates the limits of algebraic equations. An algebraic root is a physical necessity of geometry. It is the point where the polynomial mapping and the origin are forced to collide. First, retractions define absolute geometric limits. Second, these limits force stationary fixed outcomes. Finally, these spatial laws guarantee algebraic roots. For more rigorous derivations following classic mathematical texts, subscribe and join the next deep dive.